All right, so we're going to go to HFSS here. Make a new HFSS design here. There we go. And we go to HFSS solution type. We make sure it's set to terminal here. Click OK. Then let me just save this really quick. So I'll just save this here. I already have one called Sinuous, so I'll just call this Sinuous 2. All right, so let's just get to designing. So again, we go to HFSS, design properties. We need to add all our variables. So let's just make alpha. Again, alpha is an angle. So we'll just put the angle we want, let's say 35. And if we want to convert it to radians, well, we just, that's just going to be, I believe 180 over pi. Yeah, I think that's correct. Oh no, it's pi over 180. Yeah, and that converts it to radians. So that's alpha. And then we want delta. So delta, again, we just multiply by pi over 180 here. Then we also want tau. So tau, let's just make it 1.3 for now. And then what else are we missing? We have tau, alpha, delta. We also want n. So n, let's just make it 6 for now. We also want r naught. R naught, let's just make it 1 millimeter for now. R underscore end. R underscore end is going to be r naught times tau to the capital N. All right, and are we missing anything else? Let's also put in NP for number of points. Let's just say that's 1000 for now. And let's also put in our angle 1, which is just pi over 2. And that helps us make the third and fourth sinuous antenna arms. All right, and I believe that's all we need for now. So let's get into how to make the sinuous arm. So we go to our draw equation-based curve here. So x, of course, we're doing this in Cartesian, is going to be, remember that sinuous antennas, the independent variable is the radius, the magnitude. So our start underscore t is r naught, our end underscore t is r underscore end. Points, let's just use np for number of points. So that means x of t is the radius times cosine of the angle. So our radius is, of course, underscore t. It's the independent variable. So let's use underscore t times cosine. And what is the angle? Well, it's that very large equation that we put the radius into. So I'm just going to copy paste it from MATLAB here. Right here. So we have to change log to ln here. And we have to change r here to underscore t. And then y of t is just the same thing. Y of t is just the same thing, but we use sine. We use sine right here. Z of t, let's just keep it 0. We're working on just on the XY plane where Z is 0. We click OK. And all right, so we have our first edge here. So I'll just call this arm 1 underscore 1 and hit OK. Then I'm going to go to the function again, and we still have everything here. So I'm just going to go ahead and start making the second arm too, just by making everything negative. So again, just make everything negative here. I don't think I need to add all these parentheses. I'll just make it negative here. Yeah, and then we'll click OK. And we'll call this arm2 underscore 1. All right, so let's start by making the other edge, the second edge of these arms. So to make the second edge, we just make delta negative. So we go over here, we make delta negative. We go over here, make delta negative. All right, there's our second edge right there for that one. Hit OK. This is arm2 underscore 2. And go over here, let's get rid of this negative at the beginning and the parentheses at the end. Then over here, let's get rid of the negative at the beginning. All right, and there we go. We have our, this is arm1 underscore 1. All right, so Kareem, looking good so far here?
This is looking amazing, man.
Yeah. So this is we don't have to. So again, we're not going to use the antenna toolkit here. We're just going to make our very own robust design where you can change the variables and the design properties here, because the toolkit is just, I think it's very limited. So that's what we're doing here.
I agree. I've used it and it is very, very limited.
Yeah. So. All right, so now that we have our first two arms, let's just make our outer bounds and our inner bounds for these arms here. So I'm going to go to the line function just to copy paste this whole big formula here. All right, and because we're going to go into our variables and we're going to make our phi end and our phi starts. So phi1 underscore end is of course going to be this positive delta here, but we plug in r underscore end. There is an error here. Oh, we have an extra parentheses at the end here. So we have extra parentheses at the end. Get rid of this negative. We plug in r underscore end. There we go. I'm going to copy paste this because we're going to make phi2 underscore end. Paste this here, we make delta negative. And there we go. All right, so now that we have that, yeah, now that we have that, I think we're going to do something very interesting with our create line function here. Or actually, let's just make more steps here. So we're going to make our x1 underscore outer bound here. So x1 underscore outer bound is of course going to be r underscore n times cosine of phi1 underscore end. And then our y1 underscore outer bound is r underscore end times sine of phi1 underscore end. Then we're going to make our second x coordinates or Cartesian coordinates. So we're going to do x2 underscore outer bound is r underscore end times cosine of phi2 underscore end. Then y2 underscore outer bound is going to be r underscore end times sine of phi2 underscore end. And okay, wait, actually I made a mistake here. We actually don't need all of these variables here. So I'm going to I'm just going to select all of them, or I can't select all of them. So I'll just select them one at a time. Okay. All right. So the way we're going to make our outer bound is we have our phi1 underscore n and our phi2 underscore n. And we're going to go to our make line function or equation-based curved function. So again, we're just going to use r underscore n times cosine of phi1 underscore n and then r underscore n times sine of phi1 underscore n. Or no, wait, it's supposed to be underscore t here because our angle is the independent variable at the moment. So this is underscore t, z is 0. We're just on the z equals 0 plane. Our start t is phi1 underscore n, and our nt is phi2 underscore n. This is how we do it. And now we have our very nice outer bound here. So this is arm1 underscore ob for outer bound. And now just to make our second outer bound for arm2, we just make these negative. This is negative. This is negative. There we go. There's our second outer bound here. So this is arm2 underscore outer bound. All right, so we have that. Now let's make our inner bounds here. So if we want to make our inner bounds, well, let's just say we have to find our phi1 start and phi2 start. So phi1 start is going to be, I'll just make it right here, phi1 start, phi2 start. So phi1 start is going to be this, but instead of r underscore n, we're going to plug in r naught. And phi2 start is the same thing here, but it's negative delta. There we go. And now is where we're going to make our x and y Cartesian coordinates. So we're going to call this x1 underscore inner bound. IB for inner bound is r naught times cosine of phi1 underscore start. Y1 underscore inner bound is r naught times sine of phi1 underscore start. And our x2 underscore inner bound is r naught times cosine of phi2 underscore start. And then our y2 underscore inner bound is r naught times sine of phi2 underscore start. All right, so now that we have those, we're going to do something very interesting with our create equation-based curved function. So we're going to say, so we're going to vary underscore t from -1 to 1. And we're only going to use 2 points. So we're going to say that we have x1 underscore inner bound when underscore t is +1, and then we'll make this negative. And then we're going to do x2 underscore inner bound, or IB, so it's not IN, it's IB, times underscore t -1 here. Oh, I accidentally put underscore here. This should be parentheses. All right, and then I'm going to copy this and put it here, but instead we're going to put y here. And all right, right, just a second. I seem to have made some kind of mistake here. So the way I'm trying to do this is I'm going to make it that when underscore t is at the first value, we just get one set of Cartesian coordinates, and when it's the other value, we get the second set of Cartesian coordinates. Okay, I think I know what to do. I think we have to make these ones negative here. Nope, that wasn't it. Or I have to make these 0.5. We have to use 0.5. And I accidentally put comma here. All right, so when we're at negative 0.5, we want to be at this first x1 here. So we're going to put underscore t minus 0.5, and we're going to make this negative. And then we're going to make this plus x2 underscore inner bound underscore t plus 0.5. Yeah, so this part will be 0. This part will be x1 underscore ib times 1. So we'll get this first one. And then I'll just copy paste this, and we'll make these the y parts. Now we can see here we have our very nice inner bound. So does that kind of make sense, Kareem, what we did here?
Yes, so far it makes sense. Yes.
Yeah, so when we plug in negative 0.5, well, these two terms will go to 0, and then we'll get to negative 1 times another negative, that's just 1. So we just get this set of Cartesian coordinates. And then when we plug in 0.5, well, these terms will go to 0, and then 0.5 plus 0.5 is just 1. So we get these set of Cartesian coordinates. Does that make sense?
Yes, also really helps to see how you think about it as well.
Yeah. So we have our very nice inner bound here. Let's click OK. So this will be arm1 underscore IB for inner bound. And again, if we want to make our second inner bound, we just take this whole thing, put it in parentheses, make it negative. Same thing for this side. Well, we can see it doesn't matter because it's also, we can see it doesn't matter here because I think it's right here. Yeah, this one. Because the y parts are the same. So let's just be redundant here. Yeah, we can see that it doesn't matter if it's negative or positive, the y parts are the same. So let's click OK. You can see, call this arm2 underscore inner bound. All right, so now with our two arms here, we can start combining them. So we have arm1 underscore 1, arm1 underscore 2, arm1 underscore outer bound, and arm1 underscore inner bound. Let's click unite here. We unite all the lines. Let's unite all of these two for arm2. If everything is well connected, then we should be able to create cover lines with no problem. So we go to edit surface cover lines, and there we go. We have a very nice plane here. Let's do that for the other one. So edit surface cover lines, and no problems there. All right, so that's our first two arms. So far, everything seemed good to you, Kareem?
Yep, everything is perfect.
Yeah, everything's coming along very nicely. So let's just make our third and fourth arms. Let's just get that over with. So for our third and fourth arms, I'm just going to copy paste this. I'll take this. Again, for the last two arms, we just need to add our angle 1 pi over 2 to everything. So let's take this. I'll need to put n parentheses here, because this is r or underscore t times cosine of all of this. And We need to put underscore t here. Using right parentheses here. We need another right parentheses here. Yeah. And then I'll just take this, copy paste it over here, make this sign right here. And again, if we want to, over here, right next to delta, we want to add our angle 1. So angle 1 plus delta, angle 1, this will be angle 1 minus delta here. Our start underscore t is r nod. Our end underscore t is r underscore end. Number of points, let's just use np here. And all right, it looks like we have a small problem because I don't think that's how it's supposed to look like. Yeah, that's not right at all. So let's look at this, see what the problem is. Oh, what happened? All right, that seemed to be like a history button. So this is angle 1 plus delta plus alpha times sine of pi natural log of underscore t r nod, tau here. Oh, this negative shouldn't be here. Okay, let's just cancel and start over here. I don't know what went wrong there. So let's just take this. All right, let's go to our equation-based curve here. Let's start by deleting all this. So our start underscore t is r nod. Our end underscore t is r underscore end. Number of points is np. Z is 0. So x is going to be underscore t times cosine of this stuff here. But we need to add angle 1 plus this. This is underscore t. And we need to take all of this here. Copy paste here. We need to make this sine. Okay, that's the thing. This was supposed to be, they were supposed to be the same delta because we're dealing with one edge at a time. So there we go. Now we have everything. Click OK. This will be arm 3 underscore 1. And then we just need to make delta negative here. And there we go. So this is arm 3 underscore 2. And again, if we want to make our arm 4, well, we just take these and we make them negative here. So let's just make it negative here. Negative here. This is arm 4 underscore 2. And then we need to make a delta positive here. And there we go. That's arm 4 underscore 1. Alrighty, so we're very close to the end here. We just need to make our outer bounds and our inner bounds. So outer bound, of course, we need to go to our variables. I'll just copy paste this here. So this will be phi 3 underscore end. Phi 3 underscore end is angle 1 plus all of this here. Click OK. Phi 4 underscore end is just all of this, but minus delta. All right. So yeah, we have all that. Now we just go to our make equation here. So our start t is going to be phi3 underscore end. Our nt is going to be phi4 underscore end. Our x coordinate is r underscore end times cosine of underscore t. And then our y is the same thing but sine, or the same thing but sine. There we go. And there we go. We have our very nice outer bound here. And to make for the other side, we just make this negative here. Or I don't think we need extra parentheses. So make this negative. Make this negative. We have our second or fourth outer bound here. So this one is arm3 underscore outer bound. And this one is our arm4 underscore outer bound. All right, so now we just need to make our inner bounds. So to make our inner bounds, we have to make a whole new set of phi starts and x and y's here. So we'll call this phi3 underscore start and phi4 underscore start. So phi3 underscore start is right here, but instead we plug in r nod. And right here, but we make this negative delta. And then to make our x and y's, let's call this x3 underscore inner bound. Then we'll have y3 underscore inner bound, x4 underscore inner bound, and y4 underscore inner bound. So I'll just copy paste this. So this is phi3 start. We take this. This is going to be sine here. Take this. This is going to be phi4 start. Take this. This is going to be phi4 start. All right. So now we go to our create equation here. So we're going to make this our start underscore t negative 0.5. Make our nt 0.5. This is going to be just 2 points. So again, we want to start at x3 underscore inner bound. So to do that, we do underscore t plus, not plus, minus 0.5. But we make it negative here. And we'll do plus x4 underscore inner bound times underscore t plus 0.5. And we take this and we make this the y coordinates instead. There we go. We have our very nice inner bound there. So this is arm3 underscore inner bound. And finally, we're almost done here. We just make everything negative here. We have our fourth inner bound here. So this is arm4 underscore inner bound. All right, so now let's just combine everything. Let's combine everything that's arm3 here. Unite. Everything that's arm4 here. Click unite. Let's see if our cover lines work. So we take this, go to edit, surface, cover lines. And we get our very nice plane here. Take this, edit, surface, cover lines. And there we go. We have all of our arms here. And so this is pretty much all I wanted to cover right now. So we can, for example, let me change all these colors here. So let's make this, let's just make this one blue. Let's make arm2 also blue. Or right here, blue. Let's make arm3, let's just make it white. So what you would do is you would, because I made the inner bounds just straight lines, you could connect, just make a rectangular shape. You can connect sources to them. And once you connect sources, you probably have to extend the source in the Z direction for the second set of sinuous arms. Is that right, Kareem?
That is correct, so that they do not intersect.
Yeah, so they don't intersect. And so if you wanted to, you can also make a substrate. So for example, like this right now, let's call this substrate. You would make this FR4 for Dr. Jackson's team. Let's just make this green for now. And let's change create cylinder. Our radius is R underscore sub, which is just, let's make that 50 millimeters, our height. Let's just say it's negative H underscore sub, which will make 0.8 millimeters for now. Number of segments will make NS. Let's just say that's 200 for now. So right now our antenna is very small. So let's see what we can do to make it bigger. So maybe we can increase number of turns here. So let's make that 10. Maybe increase our tau. Let's make this 1.35. Let's see what happens. All right, it's a little bigger here. Let's change N to 15. All right, way too big. Maybe 12. All right, that's decent. Just because on a CubeSat is 100 by 100 by 100 millimeters. So this is typically the size you want to make the antenna, maybe smaller if you could. And so, yeah, so now that you have that, for example, we can go zoom in here. We can make a source. We could just make an antenna, make the rectangular source like this here. There, we don't even have to do any resizing. We could just say this is a source. Make this yellow. All right. And then if we wanted to start simulating this, well, we would assign each of these arms right here, assign boundary and perfect E. So for this one, for this one, for this one, and for this one. And there we go. And we would assign the source as excitation port, lumped port. Just choose one of the arms as a reference. In this case, we just have two arms attached to the source. So yeah, and then you would set up your analysis here. So auto. So Kareem, are sinuous antennas supposed to be broadband?
Yes.
Yeah, they are. So you would do, we would make this discrete. You would probably start from 1 gigahertz to 10 to test its range. We could change this to linear step is what I like to do. So that way we're stepping among frequencies here. So let's change this to like 0.1, 91 points defined. And then you would also create your radiation box. You can do this pretty easily by right-clicking the grid behind here. Go to create open region. Operating frequency, you want to put in the lowest expected frequency that you expect your antenna to work. So let's just say 2 gigahertz. And it automatically creates your box for you. And that's pretty much everything you need to know about making the sinuous antenna in HFSS. Kareem, is there anything you think that needs to be said?
I just had a question for you. So right now with the arm, if I were to change, for example, the tau or the alpha, I would not have to worry about any outer or inner bounds, right? Because you have it united. So the entire thing would just adjust, right?
Yeah, it's a very robust design. So like we can change like tau, for example, to 1.2, for example. So we could change tau. What else do you want to change?
Just tau or alpha, or just if you change any of those different.
Yeah, tau or alpha. We could change to like 20 degrees. 20 might be maybe 25. Click OK. And we can see the design holds together.
That is perfect, yes.
Yeah. So all you need to do, maybe you have to change you have to change like the source. You can see the source here didn't change size. That's just because we made it spontaneously without
Correct.
the variables.
But the arms are all perfect. You just
Yeah.
don't have to worry about them.
Arms are of course very robust, so you can change all the variables you want, and that's it will hold together. So does that all make sense?
That makes perfect sense, yes.
Yeah. Anything else that I might have forgotten?
No, man, that is amazing.
Yeah, so this is all I have to say about sinuous antennas, and I hope it helps everyone who watches.